Thinking of building a collider around the moon, if I compare the moon to the Earth and think about the advantages of each, as far as I can tell, the Earth has better staffing and proximity going for it.
Yes.
So what has the moon got going for it if we're going to build a particle accelerator there?
So the one thing that I think that the moon has over the Earth is, because you're absolutely right, the first order objection you would have to the moon is like, why not do it on the Earth? The Earth has a larger circumference than the moon. Why bother going to the moon? Find me one great circle around the Earth that is politically non-fraught. Is it possible? If you can find one, that's great. But I haven't been able to find one. I'm like, is it going to go around the oceans? And how are we going to deal with piracy? How are we going to deal with people trying to blow it up because they don't like it? What people decided? I can't find this around the Earth. So the moon is international by treaty. Well, some people haven't signed the treaty, but but in principle, that's what it has going for it, is that it's completely not politically, it's relatively politically non-fraught. And it would get us to 11, because to my mind, unless somebody were to come up with a concrete prediction, is like, if you do, the moon collider, that gets you to in my very naive estimate, 30,000 TeV, but then the Earth one would get you to, whatever it would be, 100,000 TeV. Oh, that's where the new physics is going to be. No one has that guarantee, like that precise of a prediction. So 30,000 TeV, to my mind, would really be able to, kind of settle the question for a lot of these big open questions.
So, does anybody have questions? So we have one at the back there. Yes.
Do you actually need the ring? Could you just take a suitable detector and a suitable target and wait for the cosmic rays to arrive?
It's a very good question. The answer is that yes, you could do this. So if I mention, as I mentioned, there are much more energetic collisions that happen all the time around us, and even very close to us in the upper atmosphere. So maybe not even the moon. Why don't we just take? I say these are happening in the upper atmosphere. Have some satellite and let it sit there and collect these collisions. The problem is statistics. Once again, we need a very, very, very high number of collisions to hope to discover any kind of signal for the new thing. And by a very high number, I mean that we have to collide particles at the LHC like quadrillions of times. And so the Higgs boson, we collide particles 40 million times a second, and let's say we do that for an entire year. I forget what it is, but there's only like a handful, like a few thousand Higgs bosons we produce each year. And it's impossible for us to determine whether we've discovered something and distinguish it from just a fluctuation unless we have a very high, high statistics sample. So for the production of these particles that may have only existed a fraction of a second after the Big Bang that we need to recreate in a laboratory, we have to have very, very high statistics. For things just to discover the evidence of dark matter going through us all the time, colliding with us, this is, we do use satellites for this. We use, there's these indirect detectors like the AMS experiment, if anyone's heard of that. It's a satellite that sits there and waits for dark matter to annihilate and give a little signal. So you could do this, but to discover the particles that that we're looking for in such collider experiments, you don't have enough. You'd have to wait for, I think, probably longer than the age of longer for as long as the Earth has been alive or been around to get enough statistics to determine that from just cosmic rays.
We had a question here. Please. The gentleman in front.
Just picking up what Simon was saying there, what was one of the advantages that I thought about having it in the moon? You want a vacuum and you want low temperature. How about building it in the shadow on the dark side of the moon in orbit?
Yeah, very good question.
What sort of size could you get, and what sort of answer would that give you?
Yeah, so that's a very good question. And in fact, that's a calculation I have not done. So to be completely candid, the idea of this thing like building a particle collider around the circumference of the moon, this was sort of like a tossed-off idea that came out of nowhere. Somebody was asking me about different things that I might want to talk about, and I kind of wrote this down as a thing, and then they picked that one, and I'm like, oh crap, now I really have to talk about it. So then, as I started thinking about it, I went through some of the thought processes. Gedanken experiment and, to see the feasibility of it. And I really have not done, as you can see, concrete calculations as to what we would need. But it's a very good point because, as I mentioned, we have to keep the magnets in the LHC colder than outer space. So they have to be superconductive. And to get superconductivity, you have to be at 1.9 Kelvin, where outer space is 2.7. But 2.7 is not enough. It's that extra part where you'd have to, if you want to use superconducting magnets, then you have to have the superconducting part, and you need the, I think one of my bullet points in this, everything else I haven't thought about yet, is a huge store of liquid helium to be able to do that. That's going to be a tough one. But we have discovered a big store here on Earth, so maybe there's hope. Maybe there's liquid helium somewhere, some big reservoir somewhere. But the question is, would we be able to use room temperature room? Would we be able to use just space temperature magnets and still get a decent bending power? That's a good question. I don't know what the answer to that is. It would get good enough bending power and get up to an energy that would still allow us to, into this range, this kind of like large step to really answer the question definitively or not. So it's an open question, but it's a good idea.
Also the vacuum. I mean,
yeah, I think yeah, sure. No, that would definitely help. Yeah, for the chamber for sure.
We had a question, gentlemen.
Yes.
So, though you'd said about it would cost, was it 1.59 trillion or 1.9 trillion to make the tunnel on the moon?
Yes.
Logistical issues. If it costs, say, I think when we watched in Grandstands, it was like 60,000 to build something on the other side of a river. What would it be like to get the stuff to build it onto the other planets?
You mean get the materials to the moon to actually do this?
To do it, yeah.
Yes, very good question. I think you should do this calculation. Well, like I said, this is one of those absolutely essential questions that needs to be answered if you wanted to make a concrete proposal as to how much it's going to cost. But like I said, the kind of trends and the threads are toward making these things cheaper and cheaper. So I think, for example, that Elon Musk, the name is going to come up eventually when you talk about digging tunnels. The boring company is they're trying now to beat a snail because they're actually they want to be able to dig a tunnel faster than a snail goes. So this is going to take a long time, but it's going to take some innovation to really get the speed to a point where. Speed to a point where you could do this within a reasonable amount of time. Because the thing that some of you should immediately have come to mind, I hope somebody was going to ask a question about this, is that it's not just the scaling up of the cost of the tunnel, it's the time. If it took the LHC tunnel, it was used for a previous experiment that was in there before called LEP, and it took them about 5 years to build that tunnel. So you can do the calculation yourself. That's about 2,000 years around the circumference of the moon. It's not going to happen, right? So we need some kind of advancement in that direction. In terms of getting the resources there to dig it, that's totally an open question. I have no idea how much it's going to cost. But one thing you might imagine is doing the mining on the moon, and you might have a lot of the resources that are there to be able to do the manufacturing on the moon, right?
Save quite a bit by making moon concrete. Infinitely large amounts.
Yeah, right. Well, that's another very good question. I mean, the other thing that I mentioned on this when the red X's came through, right? It's like maybe we don't need a tunnel. Maybe we could get away with something on the surface. Why do we need the tunnel? Get it on the surface and then maybe build a little bit of a shield around it with moon concrete, perhaps. I like this idea. I don't know. This is a really good question.
Okay. Yes, gentleman in the front row, white top.
And if anybody has questions in the back, please raise high. We don't want to forget you just because you're in the back.
Thank you very much. I really enjoyed the talk. I wondered if it's maybe because I don't understand Feynman diagrams well enough, but you had that Feynman diagram up and two of the particles seem to be going backwards in time. Could you explain that maybe?
Yeah, so this is a different interpretation of the sign of, it's a different way of, it's really interesting because in that, how to say this without being too complicated. Richard Feynman was really fascinating because it wasn't Feynman, but some people before him, they demonstrated that you had a certain term in the equation for a certain particle. It says that you have to do this thing called a propagator. It tells you what happens as it goes from time equals 0 to time equals whatever. And so then there's a little sign in there, and the sign can either be positive or negative. And so people thought that, oh, wait a minute, this positive sign can actually be on the energy of the particle, and that's really weird. It doesn't make any sense to have negative energy. And so then people are scratching their heads, like, well, wait a minute, what if we interpret this as an antiparticle is something that is a particle that's going backwards in time? And so it's really a bookkeeping idea. It's not really going backwards in time, but in terms of the equations, you can interpret it that way. You can put the sign on the time instead. So, for example, a positron, or this antiquark, is really a quark that is going backwards in time, but we experience it as an antiquark. That's the very short explanation that I can give you. I encourage you to.
Thank you very much.
I encourage you to go through the 6 years of quantum field theory calculations, and everybody in the audience, if you have a chance, to really understand the beauty of particle physics at its core. I'm not going to lie to you; it's really enhanced by doing 6 years of quantum field theory calculations. But you can get a sense of it without doing that, so don't worry too much about it.
I can vouch for that.
Yes, exactly. Yes, there we go.
We have a question, a gentleman in the blue top over there.
Yes.
I wondered about fate of some particle collider once a bigger one is built. I mean, I can kind of understand that you can abandon a particle collider, which is, I don't know, 5-7 kilometers in circumference, even 27 kilometers in circumference. What are you going to do with Moon collider once it's gonna get kind of expired once you build a bigger one?
There are a lot of things. That's the answer. Because this has happened in previous experiments that have been decommissioned. You can use the pieces for other types of experiments in a practical sense, right? For example, Babar. There's the Babar experiment, which was at SLAC, which did some fantastic transformative work, and then the funding was pulled for it. A lot of the pieces there can be used for other things. At the LHC, the detectors have been used, repurposed, for the old detectors at LEP. A lot of the pieces were repurposed for new detectors. In terms of the tunnel, I'm not exactly sure. For example, if you built a tunnel around the circumference of the moon, what would you use it for once the experiment would be done? Why would you stop the experiment? Just let it run. I mean, if it's automated, just keep going. I said more statistics is better. Just keep it going for centuries. We build up a very large data set. We're looking for extremely rare. I hope that's the thing you're really understanding here. Is it's not just the high energy. It's rarity. We're looking for signals that are extremely rare. That's why you have to have quadrillions of collisions to hopefully find, just a handful of events that indicate that you've seen something new. Because the things we're looking for, these phenomena, almost never happen. This notion of dark matter, if dark matter is a particle going through you all the time, you've never felt it. That doesn't mean that it doesn't interact. It means that it interacts with us, with regular matter, almost never. So we need to have huge, and this is what they do to detect dark matter. They take a noble gas, and put it in a big canister, put it down in the mine underneath the ground, and let it sit there to shield it from cosmic rays, and let it sit there for like a year. And so then if you have this volume with a certain type of atom in it, and you see no events for dark matter hitting it per year, that doesn't mean that dark matter doesn't exist. It means that it interacts less than a rate of 1 per year. So then you run it for 2 years, and that gets the rate down. So you hope to eventually find where the dark, find some signal that could be indicative of dark matter. Yeah, so we have to build up a large number of statistics. So I would say just let it run and don't shut it down. Just you get the budget to keep constant maintenance for ad infinitum. The other thing you might be able to do is mushroom farms. So I see this as a bit of a joke, but in Texas, there was the plan, I think maybe some of you know about this. In Texas, it was planned in the 1990s to have something called the Superconducting Supercollider. This is the SSC. And this was going to be bigger than the LHC. And then it was shut down because of political crap in the United States. But they had already started to dig the tunnel. And so there's a big portions of the tunnel that were already there. And I think somebody's using them for mushroom farms now. So, on the moon, I'm not sure how there's moisture for mushrooms. But
the US does have a $1 billion underground mushroom farm from the X-tunnel of the Superconducting Supercollider. I'm aware I've taken a lot of questions from the front, so yes, the lady in the white top.
We should all make sure to get this one here too. Just throw it, you can catch.
You have mentioned that it would be simpler to build it on the moon rather than the Earth due to the political issues. But wouldn't it make more sense, and wouldn't it also be cheaper and more convenient to try and convince the countries and like pay them the money, I guess, rather than spend more money by trying to transport everything to the moon.
Yeah, it's a very
And,
good
like,
question.
Choose the, I guess, more like European countries or the countries that would like agree to do it.
Yeah,
rather
that,
than,
that's a good question, right? So imagine just taking, if what I want is 11,000 kilometers around a circle, just find some circle on the Earth, you know, and you know, use your Google Maps or whatever and try to figure out exactly where's the least politically fraught place to put that. Totally a good idea. I don't know the answer to this. It's entirely possible you could do this, but my first order guess is that's still going to be extremely difficult to do. You'd have to go, one thing that I don't really know how you do, let's imagine the perfect, you know, you still wanted to get like 11,000 kilometers, and some of it went over the ocean, and some did not. Do we dig, you know, into the Earth and then also go a little bit into the ocean, and part of it's in water, and how much is in water versus the stuff that's on the or underground? I don't know, but it is really good, and I think you should do this study and let me know if you find the circle. Then I'll change my tune.
So I'm going to come to the young lady over here, and then the young gentleman over here.
Is it possible that by the time we have the material and the ability to get a large collider to the moon, we'd have invented one that doesn't require as much space with a higher energy?
Entirely possible, yes. So this is, once again, a calculation that I have not done, but you might imagine that using, for example, you know, as mentioned, that we have to have these superconducting magnets to bend protons around this 27-kilometer ring. It's because protons hate to bend. They're big, heavy beasts, and they don't like to bend. Electrons and positrons, not such a big deal. Electrons are point particles. It's easy to get them to bend. But protons hate to bend. And so you have to use really, really strong magnets to get them to bend, to keep them going faster and faster around this ring to get up to high energies. But you can use stronger magnets, and that gives you a better bending for, that gives you easier to bend with the same you know collider circumference. Circumference, and so that's one thing we're thinking about now at the LHC. We can get to 13 TeV right now with the strength of the magnets. For one of the hypotheses, or one of the postulates right now, is that why, you know, instead of an FCC like a 100 kilometers around, should we as an intermediate step just put completely new magnets in there that are like 10 times as strong? That would get us to, you know, up to like 3 or 4 times the energy, right? And so I'm not exactly sure. That's on my to-do list for this summer. It's like I've just because of, you know, doing a talk, preparing for a talk like this, and being asked to give talks like this other places. It's like I've started thinking, I probably should get a few key people together and do a white paper, just so we can really understand exactly how impossible it is. It gets back to that impossible part, right? Is it insane impossible, or is it just regular impossible? Because regular impossible we can do within a few years. So that's one of the things we'll answer hopefully this summer if we can find some free time. Would it be easier to just, you know, really invest in really strong magnets and use, you know, the 27-kilometer tunnel or the 100-kilometer tunnel to get us up to a high enough range? And would it mitigate any kind of insane idea of transporting stuff to the moon? But the moon idea is really cool, you have to admit.
Please.
How does M theory and string theory relate to what you've been talking to us about tonight?
It's one of the key things that would be revealed if we were able to get to the Planck scale. So we think that we would have to go very, very, very high to be in a particle collider experiment to be able to determine if there's substructure within, say, an electron. Because that was the question. That's very good. And the other answer to the thing where I said, you know, or the secret answer when I said, can we cut an electron? I said, no, based upon our current understanding. That's entirely possible. There's still substructure down underneath there, which is what he's getting at. What's your name, by the way? Luke. So it was one of the things that Luke is getting at, right? Is like there could be substructure within that point. It's just we don't currently have you know, a collider. Well, because really what we're doing is with the LHC, it's not just a microscope; it's a femtoscope. And if we needed, it allows us to see to a certain precision. But if we get to higher energies, we'd be able to see even smaller and smaller. And it's possible there is substructure down inside an electron or a quark or something. But some estimates say we would need to go almost to or all the way to the Planck scale to be able to determine this. So with current collider experiments, even, you know, the FCC or a moon collider, it's basically impossible. We would need new ideas to figure out how to test string theory. Because string theory, once again, is a fantastically awesome idea. We need to have concrete, testable predictions.
Is there anything special about strings, or would it just be another layer in the quantum world?
It would be one. I mean, there's nothing special about strings except that that's a way you could have an extra layer of substructure inside there, right? If you see something from a distance that looks like a point, it looks like there's nothing there. You get closer and closer, there could be stuff inside. It could be a weird-looking shape, right? But it could also be just very simply like a loop of string. Have you read Brian Greene's book?
I'm halfway through.
The Elegant, okay, yes, cool.
Yes, sir, at the back.
Thank you. With Higgs turning up in sort of an unexpected area, how confident are we that our current detectors can detect all these transients, or is there a potential for us to miss some of them and only detect the end results?
You mean the supersymmetry particles, or you mean the decay product of the Higgs boson?
When the protons collide,
yeah.
If there's transients coming out, how confident are we that we can detect all of those particles that are coming out, or is there a potential for some of them to be hidden behind the curtain, so to speak?
I'm not exactly sure what you mean by transients, but I think what you mean is that, is it possible that there's discoveries that we're missing that's kind of in that fuzz, in a way? Because this is another example of fuzz, right? Because we have more or less, we have optimized our detectors, our existing detectors at the LHC, to be able to be sensitive to collisions that have really identifiable stuff coming out, like that first one with the red fuzz, and then the two bling things out at the side. Those two yellow things are good. We can tag those immediately. But it's true. What if the new discovery is in the fuzz? We're screwed, I mean, so we're not, we're screwed. because it could easily be in there, but we're not optimized to find it. So in terms of a possible peripheral discovery that we're not optimized for, that is a lot of what I do in my research. Is in addition to, so Simon mentioned that I do a lot of exotic particle searches. I search for things like dark matter or dark photons or new force carrying particles or dark QCD, these very kind of arcane things. But really, it's more this kind of map maker and this cartography mindset. It's like we're not hunting the Higgs anymore. We found the Higgs. We're not hunting just dark matter. We're not hunting a supersymmetry particle. We need to map out all the possible places and rule out. We need to reduce to negligible the possibility that we will miss a new particle discovery at the LHC. And so one of the things that we've been thinking about is looking more closely at the fuzz. Maybe this background fuzz, we could do something a little bit more complicated with machine learning and artificial intelligence techniques that we don't use to the nth degree like private industry does, because we don't really need them. That's one of the things about you might say, ooh, CERN, must be on the, CERN research must be on the forefront of artificial intelligence and machine learning techniques, in research, and we're not, because our data set is structured very different than what a lot of the biggest advancements in deep learning, in this kind of like, Facebook, DeepMind, and whatever these things are doing to look for correlations amongst unstructured data sets. We know kind of more or less what we're looking for. So we do use some of these techniques in certain places in our data analysis, but we don't really need to use them for the hottest and latest cutting edge things, except in cases like this. What if there's something we're missing in the fuzz? And so some of us have been thinking in that direction recently, and we'll probably make some strides in that in the next few years.
Yes, sir, the young gentleman with a tie.
Would it be possible to build it as a ring around the Earth and then use it as for commercial use, so putting satellites and things like that on it, so it has other uses, but then so it can be sold as that, so possibly to attract more investment and to make a bigger ring? So
you mean like a ring orbiting the Earth, so not like on the surface of the Earth?
Yeah.
Yeah. That's a tough one. I don't know. I mean, I guess it's possible. The question I would have is, what could it be used for commercially close to the Earth? So you mean like you'd hang some satellites on it or something like that, or like Christmas baubles or something? Huh. I don't know, to be honest. Yeah, I guess you could. Okay, that's a good point. Maybe the structure. I like this idea. Maybe the groundwork is already laid because we have an ISS, right? So why not we just build a bunch of ISSs and connect them all up, right? Then we have so this to me is more in the realm of science fiction, because with a particle physics collider like this, you really need to control. The beam is very sensitive to bending and to wobbles and things like that. So I would imagine that something floating would not work as well. There are some ideas that people have had, because another question somebody should have here is like, wait a minute, why do we need to use a ring at all? Because think about what a line is. What is a line? It's a circle that's taken the radius to infinity, right? So why don't we use linear colliders? We do use linear colliders. We've used them for many things in the past. SLAC has a linear collider where several particles were discovered. But there are pluses and minuses to using linear colliders versus circular colliders. You might imagine you having like a linear collider floating in space. You might be able to, with advancements in floating RF technology, you tell me, floating in space between the Earth and the Moon, maybe you could have some kind of linear collider that would get you up to very high energies too. I don't know exactly how you do this and how would you focus it so that the beam's going out, because with a circular collider you can reuse the particles as they go around, because not all of them collide. I hope the image that you have in your mind, that's a good point. I hope the image that you have in your mind when I say that we collide protons at 40 million times a second is not like a line of ants going bing, 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 bing. That's not what happens. Instead, we have two big bunches of protons. And these bunches pass through each other. So you got a bunch, a space, another bunch, and there's space in between so you can tell when that happened. And each one of these bunches does not have just like a handful of protons. The bunch has 10 to the power 11 protons in it. And they just pass. And overwhelmingly, what happens when they go through each other? Nothing happens. They just pass through. On average, about 50 to 100 collisions happen. But think about what I said. 10 to the 11, 10 to the 11, almost nothing happens, but still 50 collisions. 50 is a lot. That sucks. I mean, we would prefer to have just one, but it was calculated that way to begin with. It's like they said, okay, what can we get away with? What can we live with? So we have these two things go through each other. Maybe about 50 collisions happen. On average, only one of those is interesting. And this is, I think, one of the slides that I had where it showed like the gray fuzz, and then the gray eventually disappeared and came down to those 4 lines that were interesting. That's what we do with our data reduction. We get rid of the background collisions. And what that means is that overwhelmingly when the protons go through each of these bunches, you can reuse the ones that don't collide. And so they just go around the ring over and over and over. With a linear collider, you can't do that. So that you have to dump them somewhere. You have to focus the beams together, and then they have to dump. And imagine it's something, a linear collider in the middle of space. You'd have to make sure it's not, aimed at, at the Earth somewhere, like a children's hospital or something. That would be really bad. Also, you have to think, about it in terms of. Yeah, we need to think of it like in terms of our, citizenship, and not just Earth citizenship, but our solar system and galaxy citizenship, or galactic cluster citizenship too. Because imagine if you had some kind of linear collider where the beams were going out like this, and you're just dumping a bunch of beams into space. And some distant civilization millions of years from now suddenly gets this weird signal. They're like, ooh, there's something there. What is it? What is it? Maybe we'd screw up their experiment too. Or maybe we'd be sending our protons at one of their children's hospitals too. It's like, I'd prefer to have a circular collider personally.
One more question from the lady with the grey hair at the back.
Would it be possible to not have a ring and not have a linear, but in fact have a coil? Would the changes in angle make it stop you having that? Because you could get an awful lot of distance in a comparatively small area. You get to the top of the coil and then you could go down and sort of to the bottom again.
That design for a collider experiment I've not seen before. I think there's some drawbacks to that because of the.
I wonder if because of the changes in, because there'd be small changes in the angle and everything.
So you're saying that the particles would go up some coil and then they come back down and then they will collide, and they'd have two of them interlocked or something like that. So then, at first.
Well, can't you sort of? You start, you coil up. You dive down again, and you join up with the bit at the bottom where you started.
My first impression is that is more or less what happens. What we do now is if you just take all those coils and smash them into one circle, because they go around many, many, many times before they collide. Yeah, so I think that's kind of just, you're taking what we do and sort of like expanding it out a bit, which I think is unnecessary. You're going to waste a lot of energy that way, I think.
Okay.
Good idea, though.
So one more question, if we have one. Yes.
Are there any up in the top that we've missed? If you're...
So I do know at this point in time, we do not know too much about dark energy and dark matter, but couldn't hypothetically these concepts and ideas, or like with the Large Hadron Collider and the CERN particle accelerator, couldn't these concepts be applicable to dark matter and dark energy if we took two dark energy particles and we put them in a collider? Couldn't that be hypothetically possible?
Well, for dark energy, that's a bit of a sticky wicket because we almost know nothing about dark energy. There's two things going on. So the first thing that I mentioned there, what is 95% of the universe made of? That's a combination of what we refer to as dark matter and dark energy. Dark matter is the thing that's with the galaxies, right? We know that dark matter exists because we see its effects on the cosmos due to gravity. But if it only interacts via gravity, we're basically screwed again because we don't, if it doesn't interact any other way, dark matter, then there's no, other than gravity, there's no way for us to really do anything about it because, gravity is extremely weak compared to the other forces. And in fact, in our particle collisions, we never even bother to care about it to think about it when we do the collisions. The other three forces we think about all the time, but the gravity is 10 to the minus 39 compared to the other forces of nature. So gravity is extremely weak. But we know that dark matter exists because of its effects on the cosmos. But that indicates that it's not just a little dark matter, it's like 5 times as much dark matter than there is us. So we're regular matter. We know that there's at least 5 times as much dark matter than there is regular matter. The rest of that other percentage is dark energy, and we have no clue what that is. I mean, we have some clues, but it's really one of the very difficult things to explain about what's driving the accelerated expansion of the universe. And there's some interesting ideas in that direction. There are actually a couple of things that are maybe new to you, is relatively new to us too. At the LHC, we can say a non-null statement. We can make a non-null statement about dark energy at the LHC when it wasn't entirely clear to us even a few years ago that we could do so. But in terms of a dark energy particle, that's very ill-defined, and I don't even know what that would be. Something that we could say anything about at the LHC. With dark matter, first we have to define dark matter, and then we can think about putting it in some kind of particle physics experiment. The challenge, though, is going to be if that's what you're asking. I hope I got the question right. If you wanted to make some kind of dark matter collider, if you wanted to design something to control dark matter to collide it, well, first you have to define it. But then the other thing about dark matter is, what is the key thing about dark matter? It's going through your body all the time. It's not interacting with you. It's not interacting with metal. It's not interacting with wires. It's not interacting with electrons. It's neutral. It doesn't interact with us at all. It doesn't have any charge. So it's almost impossible for us to it would be very difficult to make a dark matter beam. I mean, if you found it, you could. There's ways that we make neutron beams. But first things first. Let's discover what dark matter is first, and then let's talk about making a collider out of it.
I think we're almost out of time, but before we close, I wanted to just ask you one more question.
Yes.
So as somebody who designs and builds particle accelerators, each time somebody proposes some wonderful, fantastic, gigantic new particle accelerator, it reminds me of a little bit of a builder who only has one tool in his toolbox. So he's only got a hammer. And somebody comes to him and says, I want you to build a house. It's like, okay, I can use this hammer. And then you say, okay, can you make a chair? So long as I can use hammer. And then you say, okay, can you dig a hole in the ground? But I really like hammer. We recommend you use a spade. So by doing what we already know how to do, but bigger, that's one way of investigating the universe. Are we ever in danger of preventing ourselves from going in a different direction and exploring the universe in a new way when we're just upscaling, we're getting bigger and bigger, we're using hammer, we like hammer?
Yes, that's a very good point, and there is a danger that we're doing that because I wouldn't call it so much of a danger, except I would more refer to it as Okay, maybe a danger. Because I wouldn't say that it locks us into a certain mindset, though, because once again, like I mentioned in the slides, is that this has always worked in the past, and it's really the only way that we know of at the moment, to coax these particles back into existence, the ones that may have existed just a fraction of a second after the Big Bang, that we need to go to bigger, higher energy collider to rediscover, and study. And so if the new physics is a particle, and it might be represented by a particle, then this is the way to do it, because it's always worked in the past. That being said, we should not rule out other possibilities. And in fact, think about it, really. A moon collider is probably not going to happen next year. It's probably not going to happen 5 years from now. But if the LHC goes through its entire research program, and that's the other caveat, especially for any of my colleagues at the LHC that might be watching, this is totally premature. It could be completely premature, because we'll be taking data at the LHC for maybe like 2 more decades. There's very much there's still time for new particles to show up. So all of this could be moot within like 3 years, and that would be great, because new discoveries, new things to study, new ways to think about the world. But if the LHC goes through its entire research program and finds nothing except for the Higgs boson, that null result can spur us to think in new ways. We're already thinking in terms of this using a bigger hammer, going to the FCC, and I've just proposed we put something on the moon. This is even a bigger hammer, but this is once again based upon our intuition and our intuition, which is based upon experience. When we've done this in the past, we've gone to bigger colliders. We've always learned more about the universe. And if the rules of quantum field theory, work up to higher energies, then that should teach us something about nature, no matter what, whether we find something or not. That being said, I'm not sure it's a danger, but that it locks us into that mindset. But I also know that people, are not just, this is a critical juncture for particle physics, is because, like I said, our motivating ideas are kind of running out, and these lampposts as to where to look are getting dim. And so that is a little bit of a crisis, I think, for some people that have been working on this for a very long time. But for those of sort of early career, we're like, ooh, this is freedom. We now get a chance to think in new ways. And this is really the exciting part, because I'd never be so craven as to underestimate the ingenuity of humanity. It's it's like this is the time where my early physics, early career colleagues, they get to think in new ways about M theory and string theory, dark energy. What are new ideas to test these things that are not just relying upon a bigger hammer, on the moon? So I think that these are going in parallel, to be honest. I don't think there's really a danger of us getting locked in this mindset. We do this because we know that it works, and it has worked in the past. And if the new physics is to be represented by a particle in any capacity, and the rules of quantum field theory work, up at higher energies, which we have no reason to think they don't, this will teach us something. At the same time, people need to realize that we are running out of ideas, and we need new ideas. So think in new ways.
Ladies and gentlemen, will you please join me in thanking James Beacham.